All right, guys, so here we're going to look at our last one in this unit, optimization problem. So as always, we're going to begin with our bell work. So pause the video if you haven't done it and give that a try. And if not, or if you have already done it, great. Let's take a look at it. So we want to look at a particle moving along the x-axis with a speed of this v of t function on the interval from 0 to 5. How many times to change direction? So that means we need the speed to be 0 and we need the sign to change around that. So that first one's real easy. This one's going to be at t equals 3. The cosine one is a little bit trickier. And so for that cosine of 2t, we want cosine of 2t to be equal to 0. Well, we know that cosine is equal to 0 at pi over 2 and 3 pi over 2. So what we do is we're going to then set that up with that being equal to 2t. So 2t is equal to pi over 2, which means that t is pi over 4. And 2t is going to be equal to 3 pi over 2, meaning that t will be 3 pi over 4. Now, all of these numbers are going to be between 0 and 5. So that means that now what we're going to do is set that up as a sign analysis where we're going from 0 to 5. And we're going to check it at, let's see, our first one there is going to be pi over 4. Then the next one would be 3 pi over 4. And then will be 3. And so we're going to check each of those intervals. Now, in between here, let's maybe go with like pi over 6. Here, we can go with like, oh my gosh, my brain's not working. Well, here I can do pi. Bigger than that, we can maybe go 5 pi over 6. Pi over 2. There we go. That's what we use. So there's our test points in between there. Now, why am I doing the ones with pi? Well, because t minus 3 squared is always going to be positive. So our first term is always going to be positive. We're really just worried about that cosine one. So cosine of 2 pi over 6 is cosine of pi over 3. And in that case, it's going to be positive because that's in quadrant 1. Then we're going to get the cosine of 2 pi over 2, which is cosine of pi. And at that point, cosine is -1, so it's going to be negative overall. 5 pi over 6 is really cosine of 5 pi over 3. And so that's going to be positive, because that's going to be in our quadrant 4. And then cosine of 2 pi, that's 1, so it's going to be positive as well. So then the last thing is just to check where it actually changed signs there. And so here we've got a change in signs, and here. So when we're looking at how many times the particle changed directions, it changed twice. So it changed directions twice. And if we want to be specific, at t equals pi over 4 and 3 pi over 4. Right here at 3, it didn't actually change direction, so we can't include that one. All right, so now let's take a look at our optimization problems. And we're going to start off with a few rules to kind of help us know how to tackle these, okay? So the first one here is going to be to determine the quantity that has to be maximized or minimized. Our next one is going to be that we want to sketch a picture or write let statements identifying variables, not various, variables or quantities that are not valued. So the things that we don't actually need, like they either don't have a value in them, or the things that we're going to need to get rid of, in a sense. We're going to have to use a form or a equation to kind of get rid of one. All right, write the primary equation that represents the quantity that is to be optimized. So the equation may contain more than one variable, as I was talking about, where we're going to sometimes get rid of some of them there. All right, our fourth thing that we want to keep in mind is that if the primary equation contains more than one variable, a secondary equation may need to be written to show the relationship between the two variables. Okay? The secondary equation will be used to rewrite the primary equation in terms of one variable, so that we can actually solve it. And then our last one, the last kind of like key point here that we need to realize or think about is to take the derivative and verify by a sign analysis that the primary quantity is maximized or minimized. All right, so make sure that it actually did what we were supposed to do. All right, so a manufacturer, let's put this into practice. Manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? What is the maximum volume? All right, so the thing that we, as we talked about, like, right, if our first one is determine the quantity that is maximized. Well, that is our volume. So our volume needs to be maximized. Maximized. All right, then from there, we need to come up with an equation, right? So what is our equation for volume if we've got a square base box, okay? Well, it's going to be x squared times y, where y would be my height and x is the dimensions of that square base, all right? Now, the issue there is that we know that we have a surface area of 108 square inches, and we don't want to change that. So we're going to also need to use that secondary equation now, okay? And this is where our surface area is going to be equal to, is it an open box? Yeah, open box. So we don't have a top and bottom on it. So we're going to have four sides that are x, y, plus we're going to have the bottom. We don't need a 2 here because it's an open box. There's no top, okay? Then what we're going to do is we're going to take this and we're going to solve this for y, which is a little bit awkward, but that's what we're going to do because we don't want to change our surface area. So we know that it's 108 equals 4xy plus x squared. I'm going to do this all at once, okay? So hopefully you can keep up here, but basically I'm going to say that this is 108, right, minus the x squared, all divided by 4x, and then I've got my y. Why? Because I want to plug it into there. So my actual new, primary equation, once I've simplified it, is going to be that the volume is equal to x squared times, instead of y, we're going to make that substitution, 108 minus x squared over 4x. Now, to make it a little bit easier on myself, I'm going to immediately get rid of this x with one of those x's, because when they multiply, they're going to simplify that way. So then let's simplify this equation. And so I'm going to get 108x over 4 minus x cubed over 4. Now, I could also simplify that. So the 108 over 4, let's see, that'd be 54. Half of that's 27. So it'll be 27x instead. All right, now that we've got that, our last step there was to take the derivative. And so we're going to do that. So v prime is going to be 27 minus 3x squared over 4. Okay, now again, we're trying to maximize, so we need a critical point. So we make it equal to 0. 27 minus 3x squared over 4. We can move that over. So we get 3x squared over 4 is equal to 27. And then we just start working out the steps to get rid of that. So we're going to multiply both sides by 4. And so we'll get 3x squared equals back to 108. And then we're going to go ahead and divide that by 3. And x squared will be 36. Then we'll square root that. And so x will be equal to plus or minus 6. Of course, one of those isn't going to make sense, so we're going to throw it out. The negative version is going to be like outside the domain, so we don't care about it. Doesn't make sense for us to have something that has a negative 6 length. And so instead, we're just going to be dealing with that 6. Last step we had said was to do that kind of confirmation that it was indeed maximized, like so. So we'll check a point over here, and we'll check a point bigger than it as well. Don't need that there. Okay. So then we're going to plug those in. if I plug in 1 and try to figure out if it was maxed, what the sign is, so I'm going to plug it into my simplified one. So let's put it into this version here. It's going to be 27 minus a fourth. Well, that's definitely positive. And then I'm going to put in 10. That's 270 minus 1,000 over 4, which is 250. Well, that's actually, hang on, did I do that right? 270 minus 1,000 over 4 is 250. So 270 minus 250, that's also positive, which probably means I did something wrong, which could just be my math. Let me actually pause it and do the math on my calculator quick. And that's what I get for not doing the problem beforehand. No, I'm plugging into the wrong one. We're supposed to be checking the derivative, right? Not the original volume, because if the volume was negative, that would be weird. So it should be positive. Okay, so here, let's double check again. So if I put in 1, I've got 27 minus 3/4. That's definitely positive. And then I've got 27 minus 300 over 4, which would be 25. So well, regardless, a hell of a lot more than 27. So that is going to be negative. So it did indeed change this. And we also know that very specifically it went up and then down. So it did create a maximum there. All right, so our maximum does happen at 6 for our x. Now, does this tell us what is the maximum volume? Oh, all it wants is that maximum volume. Okay. So then, kind of running out of room. This is unfortunate. I should have given a little more space. But basically, we've got that x is equal to 6. I can then use that to find my y by putting it into my surface area equation. And so let's see here. If I do that, I'm going to get that y is equal to 100. So, sorry, it'll be 108 minus 36 over 24. 108. You know what? I'm just going to put it in my calculator. Last time I did it all in my head, I made a mistake. So let's put it in the calculator this time. And I get 3. So y is going to be 3. And so then I can just work that out. So my maximum volume is going to be 6 squared times 3, which is actually right back to where we were there at 108. So it's going to be 108 inches cubed. That would be my final answer there. Okay, let's take a look at our next one. Hopefully I left myself enough room, but maybe what I'll do is I'll actually zoom in just a little bit here so that I'm writing a little smaller. See if that helps us. All right, so we got a box to be built with a rectangular piece of cardboard that is 25 centimeters wide and 40 centimeters long by cutting out a square from each corner and then bending up the sides. Find the size of the corner square, which will produce a container with the most amount of soup. All right, so the first thing we're going to do is start off with a rectangle here. Okay, and then what we're going to do is we're looking at the fact that we want to cut out squares from these little corners here, right? And we know that the piece of cardboard is 25 by 40, which means that inside here, it's going to be less, right? So if this is x by x for all of these, then that would mean that this distance inside, I have to kind of write it out here, is going to be 40 minus 2x. And this one in here is going to be 25 minus 2x, okay? So then if I'm figuring out what my volume is going to be x, the height of this box, by my two other dimensions. So by my length and my width, like so. All right, and then unfortunately, what I need to do at this point is just multiply that all out. So then I'm going to need to do that. So let's see, the volume is going to be x times, yeah, going to need my calculator. No, 25 times 40, yeah, it's 1,000. Minus 50x minus 80x, and then plus 4x squared. And then, of course, I'm going to plug in that x, so I get 1,000. Actually, you know what? Let's reverse the order. Put it in descending order, so we'll get 4x cubed. Put those together is 130x squared, and then plus 1,000x. All right, so then I can work from my simplified volume equation. All right, so then our very next step was to always take the derivative. So our derivative here is going to be 12x squared minus 260x plus 1,000. All right, and at that point, I mean, that's kind of gross. I'd probably take a 4 out of all those, because otherwise it's just kind of hard to work with. So then I'd get 3x squared, 130, half of that's 65x plus 250. That's a whole lot easier for us to kind of work with. And then from there, I still need to go ahead and factor that. Man, I'm just getting lots of lag. I don't know what's going on today. All right, so when we factor that, let's see, we need something that's 750 or 65. Probably going to be 50 and 15. Yep. All right. So that means we're going to get 3x minus 50. And then we'll get, let's see, it would have been x minus 15, but we got to divide by 3, so x minus 5. Okay, if you need help doing that, that's pre-calc, so just go ahead and take your time, work that out. Know that this is our answer afterwards, and go from there. Okay, that's our v prime still, and so now we want to make that equal to 0. Well, instead of putting v prime, let's even put 0. And so that's going to be that x is equal to 50 over 3. That's look at that lag spurt there. 50 over 3 or 5. Okay, those are going to be our two answers. Now, if I do 50 over 3, that's going to be like over 15. If I cut out 15 from both sides here, obviously that doesn't work. It's going to be bigger than my side length of 25. So clearly, this one is going to have to be thrown out because it doesn't make sense. All right, so instead now, let's just look at that 5. Let's make sure that, no, you know what, actually, maybe I'll leave that 50 in there to kind of show you just when we do our sign analysis, and you'll see why it doesn't work. So obviously our smallest there is going to be 0. Can't take less than 0. We won't worry about the upper bound, even though technically there is one. It has to be less than 25. Well, let's put it 25. Because if it's more than 25, it's not going to work. Okay, and so then we're going to put in 5, and then we're going to put in 50 over 3. Okay, so if I just choose some numbers in there, let's choose 1. If I put in a 1, I'm going to get a negative times a negative, which is positive. Here, if I put in, say, 6, let's do 10. 10's easier. 30 minus 50 is negative, minus 5 is positive, so positive and negative, so that's going to be negative there. And then if I put in something bigger than this, which will be like 20, that's going to be a positive, and so it is positive. And so you can see now why this one doesn't work. This here is clearly a max, but this is actually a minimum. And it actually doesn't even work, because like I said, if we take out, 18 inches from both sides, it literally ends up with no side. So this is actually our max, though. And so we want to cut corners of length, and was it inches? No, centimeters. Man, this lag is really killing me today. Lag of 5 centimeters. Okay, and really, I guess it's 5 centimeters by 5 centimeters would be our answer. All right, so we want that, and why do we want that? Even if it doesn't tell us to justify, it's because again, it's going to switch signs from positive to negative, meaning that it's max. All right, let's take a look at our next one here. Rectangle contains 24 square inches of print. The margins at the top and bottom of the page need to be 1.5. So let's go ahead and draw our page in here as best we can. So, and we're going to get, let's see, this is x plus 3, and this down here is going to, sorry, not, God, I can't read any of it. Y plus 2. There we go. Jeez. Horrible. Okay. Now, why is it those things? Because here I'm taking out the margins at the top and bottom are 1.5 inches. So I don't actually, like the printed area is going to be just x. And then our margins are the 3. And then for y, we got our margins on the left and right that are 1. That's going to be our part that we can't include. So if you want to think of it, it's like, oh, I can't. It's lagging so bad I can't actually draw this in with a dotted line like I'm trying. But basically the idea is that this distance here is 1.5, this distance is 1.5, and then this one here is 1, and this here is 1. So the area inside here is just going to be x times y, but the area of the whole thing is x plus 3 and y plus 2. All right, so that means that our area is exactly like I just said, x plus 3 and y plus 2. Sorry about the lag there, guys. I don't know what's going on with my connection today. And then the other thing that we know is that our area tells us that it's 24 square inches of print. So that means that xy, which is that inner part there, is going to be equal to 24. So 24 is equal to xy, which if I want to solve for one of my variables so I can get rid of it, I'm going to get that y is equal to 24 over x, and then I'll plug that in to my original equation there. So now I can create that equation with only one variable, so it's going to be x plus 3. And instead of y, I'm going to put 24 over x plus 2. And I'm going to, now that I've got that, put that together or take the derivative. It's probably a little bit easier for me to put that together rather than take the derivative first, because then I'd have to do a product rule. So let's go ahead and put it together and simplify it first. So in doing that, no, I don't know if I can. Yep, there we go. It didn't want to let me write anything. So this is going to be x times 24 over x, which is just 24. The x's will cancel. And then plus 2x. Then we'd multiply the 3 in. And so we're going to get 72 over x plus 6. Okay. And then at that point, I can, of course, put my 24 and my 6 together. So I'll get 30 plus 2x plus 72 over x. At that point now, I can go ahead and take my derivative. So if that's my area, then the derivative of my area, the 30 goes away, I'm going to get 2. And then here, this is the same as saying x to the negative 1, so I'm going to get minus 72 over x squared. All right, so then what I can do is make that equal to 0. And if I make it equal to 0, I'm going to move that over actually at the same time, because this is technically 0. So it'll be 72 over x squared, and that's equal to 2. Then, of course, I'm going to multiply both sides by x squared so that I can move it off of the bottom. I can't solve it if it's on the bottom. And then I'm going to divide both sides by 2. So I get that 36 is equal to x squared, square root that. Now, we already learned last time that I can't have the negative value. That doesn't make sense. So x is not going to be plus or minus 6. It's just going to be plus 6. Okay? Now, from there, what I could do is I could confirm that it is indeed, oh, maybe, there we go. Go from 0, go from 6. Let's check points 5 and 7. Okay, so if I put 5 into that derivative here, I'm going to get, let's see here. You know what, let's do 1. 1's easier. Why am I doing 5? 1 is way easier. All right, so 1, if it'll let me draw it. There we go. That's going to be 2 minus 72 over 1. Just trying to clean up the lag. I don't know. It seems maybe it's a little better, but we'll see. So if I plug 1 into that, I'm going to get 2 minus 72, which is, of course, negative. And then I'm going to go ahead and plug in 7. Probably easier if I did a bigger number, but that's okay. 2 minus 72 over 49. Yeah, let's make it easier. Let's put that at 10. It'll be easier for us to work out. So that's going to be 2 minus 72 over 10 squared, which is 100. 72 over 100 is definitely less than 2, so that's going to be positive. And of course, we get that minimum that we were looking for, right? That least amount of paper that's used. So that will tell us, correct? However, the question did say to find the dimensions, which means I also need to find y. So I'm going to go back to my 24 equals xy. I'm going to plug in my x of 6. and get that 24 is equal to 6y, and then simply divide both sides by 6. That's going to give me that y is equal to 4. So my dimensions are going to be x equals 6 and that y is equal to 4. All right, I am going to stop this video and see if I can fix the lag because this is just absolutely atrocious. It's very hard for me to teach, and I'm pretty sure it's pretty hard for you guys to be following along too. So I will pause it and come back with these other couple questions. All right, I think I've fixed the lag, so that way we can finish off the rest of this video without having so many problems with the writing here. So we've got a rectangle that is bounded by the x and y axes, as you can see in the picture here, and the graph of y equals -1/2 x. So what this means is that this graph here is our graph y equals 3 minus 1/2 x. What length and width should the rectangle have so that it has a maximum area? Well, if we look at this right off the bat, we know that our area is going to simply be the x coordinate times the y coordinate, okay? Now, we also know that y is going to be equal to this equation. So what we can do is take that equation and substitute it in so that our area is actually x times 3 minus 1/2 x, like so, okay? Then we can simplify that by distributing it, and so our area is going to be 3x minus x squared over 2. Then from there, I can take my derivative, which will be 3 minus the 2 will come down and cancel with the 2 underneath there. So we'll just get minus x, which of course, when I make that into our critical point, so 0, if I pass that x over, I get simply that x is equal to 3. All right, so let's do sign analysis and make sure that that is true. So we've got 0, we've got our 3 in here. All right, so we're going to put in, say, 2 and 4. You know what? Why am I doing that? Let's do 1. It's always easier. And 5, okay? So if I'm plugging 1 into that equation, down here, 3 minus 1 is positive. But 3 minus 5 is going to be negative, which is what we wanted, because the whole point is that this should be a maximum here, because we want the maximum area. And so that, therefore, tells us, literally, right? If we wanted to find, x would, of course, correspond to our length. If we wanted to find y, then we can simply plug it into that equation that we have. So we can say that y is equal to 3 minus 1/2 times our x value of 3, which means that y is equal to 3 minus 3/2, which means that y is equal to 3/2. So we get the point x equals 3, and y equals 3/2, or as a point, 3 and 3/2. Or, rather than putting x and y, if we want, we could call it the length of 3 and the width of 3/2. All right, there we go. Now let's take a look at this one here. So determine the point on the line y equals 2x plus 3, so that the distance between the line and the point 1, 2 is a minimum. So if you did any of these in pre-calc, you'll remember that this means that those have to be perpendicular, okay? And we want that distance to be a minimum there. So what we need to do is take a look at what our distance is actually going to be. So the distance between those, I guess let's use our distance formula here. So it's going to be, oops, why is it doing that? There we go. Square root of x minus 1 squared plus y minus 2 squared. Because we're trying to find this distance here, and so it's between that line and then our x, our minus 1 and minus 2 to get this point in there, okay? Now, instead of it being y here, we can change y with the equation of our line so that we're actually moving from our line. So that would mean that our distance is going to be x minus 1 squared plus, and instead of y, we're going to put in 2x plus 3. So 2x plus 3 minus 2 is plus 1, and we will square that. Now at this point, this would be a pretty annoying thing to take the derivative of, so my recommendation is going to be that we simplify that a little bit before we bother taking our derivative. So let's go ahead and do that. So I'm going to get x squared minus 2x plus 1 for that first expansion. And on this one, I'm going to get 4x squared plus 4x plus 1. Now, if we combine those, that's going to be a lot easier for us to take the derivative later. So let's go ahead and bring this back up to our top. Okay, and so when we put those two things together, we had 4x squared and x squared, so that's 5x squared. And then we had negative 2x and 4x, so that's plus 2x. And then we had plus 2, 1, so plus 2. And sorry, that's still equal to our distance. All right, and then at that point, now this is a lot easier, so now we can probably take the derivative. You could have done it earlier, but I think a little bit of algebraic simplification makes it easier. So this is going to be 1 over, and we put down the original thing with our new square root that ends up on the bottom. And of course, the 1/2 came down as well, so there's a 2 in front. And then I need to multiply that by the derivative of the inside, which is 10x plus 2. Now, you can probably already see that I'm going to have something cancel out here. This 2 is in both 10 and 2, so this is actually going to be like 5x plus 1. So now let's write it as a single statement. It'll be a little easier. So 5x plus 1 over the square root of 5x squared plus 2x plus 2. And if we want this thing to be 0, we really just need to worry about the top there. And so that means that it's going to be 0 at negative 1/5. So we can look at negative 1/5 here. And let's plug in some easy numbers, 0 and negative 1, to check it. Okay? So let's do 0 first, because that's the easiest. If I put in 0 here, I'm going to get 1 over the square root of 2, which is positive. If I put in negative 1, I'm going to get a negative on top, divided by, now we kind of know that this needs to be positive, because otherwise it wouldn't work, but we should make sure, because it is possible that it isn't, in which case this actually isn't, this point won't be a minimum or maximum. So let's go ahead and check. So if we put this in, that's positive, so it's going to be 5 minus 2 plus 2, which is 5. So the square root of 5, which is, of course, positive, and a negative divided by a positive is negative. So we did get that minimum that we were originally looking for, that minimum distance. And so this is going to have a minimum at x equals negative 1/5. And our reason, just as it's good always practice, because d prime changes negative to positive. All right. Now let's see. Did it ask me for determine the point on the line? Yeah, I need the whole point. So I'm not quite done. I need to also find y there. So if my x is equal to negative 1/5, I need to find my y. I'm going to do that by using this equation. So y is equal to 2 times negative 1/5 plus 3. That's going to be negative 2/5 plus 3, which is going to be, let's change that into over 5. So instead of 3, we're going to multiply it by 5. So that'll be 15 over 5, sorry. That would give us 3. And so we're going to get 13 over 5. So y is equal to 13 over 5. And so our point up here is x equals negative 1/5, and y is equal to 13 over 5. Awesome. All right, that brings us to the end of that one. Sorry, that one was a little choppy. I know there's a lot of lag earlier on, but we got through it at least, and you've got them all there. So see you guys next time.